Okay, hello, Discrete Math, back again the next morning, and we're going to go over the second homework from the unit on graph theory. This is the homework from section 10.2. 10.2 is all about walks, trails, paths, circuits, cycles, also connectedness, including edge connectivity, vertex connectivity, adjacency matrices. So he just threw a whole bunch of stuff all into this section. Let's go. This was the homework assignment, and it came kind of like in two parts or something, but anyway, here it is. Let's begin. The very first problem is probably the most difficult problem from the whole homework, or at least it's the most theoretical. It's the one that requires the most math, so to speak. We have to prove this theorem about connectedness. So let's go. Number 2, if G is a graph, then either G or G complement or both is connected. Okay, well, first of all, it only makes sense to talk about the complement of a simple graph. And so I think this should say simple. That's an error that he makes sometimes, Gossett, and other people do as well. So okay, so we have a simple graph, then either G or G complement is connected. Should we sort of build some sort of intuition on this? I don't know, maybe not. If your graph is, let's put it this way, you're connected or you're disconnected. If you're disconnected, then that means that there are some people who are not friends with anyone, or some people who are friends with only some of the people, and there's sort of no walks whatsoever between these two different components. But loosely speaking, you should just sort of feel immediately that this theorem is true, because here in a graph with 5 vertices, where here's this graph with five vertices where we have also just 4 edges, then what I was going to say is that there are 5 vertices. We discussed this in the previous video. There are 5 vertices, so there are 5 choose 2, which is 10 edges possible. So here there are 4 edges. So sort of somehow, we're going to get a lot of edges then in the complement graph. What does the complement graph look like? Well, now there's just like a lot more friendships, right? We have something like this, and jump, and jump. So suddenly this graph just is connected. So okay, that was pretty weak, bordering on maybe totally unhelpful. But the sort of idea is that if the original graph has not too many edges, then the complement graph will have a lot of edges. And so this theorem is just summarizing that observation and making it more precise. Let's just begin. So what do we need to do? We need to show that either G or G complement is connected. Okay, so let me just write that down. So prove that G or G complement is connected. And by the way, is it possible for both to be connected? I bet so. Yeah, here's an example. Take C4, the cycle graph. Jump. That is connected. But what does the complement look like? The complement is not connected. So I'm dumb. Let's try to do a better job. That was a sort of a little bit surprising that happened, actually. So wait, let's go up to 5. In this graph with 5 vertices, and this is connected. I'm trying to find a graph which is connected but doesn't have too many edges. I think I have finally found my answer now, right? This is connected, but now what does the complement look like? The complement looks like this. Yeah. So here's a graph, the cycle graph, the graph C5. The graph, original graph drawn in black is C5, the cycle graph with 5 vertices. It's connected. Its complement is the red graph, which is, by the way, also C5, because it's also just 5 vertices connected in order. And so this shows that it is possible for a graph and its complement to be connected. Okay, but anyway, this is inclusive OR here is understood in math context, unless you have some reason to be told otherwise. And so, okay, that was just a sort of point of clarification. But anyway, when it comes to just doing the proof, let's just, it would suffice to show that either of them is connected. So the strategy, and by the way, Gusset just comes right out and tells you to do this. Hey, suppose G is not connected. So it's kind of like this, right? If I want to prove that one of these is connected, then what I'm going to do is, suppose G, maybe even just to be even more explicit about this, it's kind of ridiculous, but so G is connected or not, or G is disconnected. So there are two cases, right? There are two cases because there's the case where G is connected and the case where G is disconnected. So case one, G is connected. Well, if G is connected, then the theorem is just automatically true because the theorem says that either G or G complement is connected. So once I've shown that one of them is connected, I'm done. This is just stupid. I regret saying this. But then what's case two? Case two is that G is not connected. Okay, so now if G is not connected, then I need to show that G complement is connected. Okay, so why is G complement connected? Well, here is where I get to now use the definition of connected. So what does it mean what does it mean if G is not connected? If G is not connected, then we know that there exist at least two vertices for which there is no walk between them. And really, we're going to now lean heavily on this analysis that we did, in class 2 weeks ago, which is that, I'll just repeat this very quickly, that we can define on every pair of vertices a certain relation. And if this is a pair of vertices, A and B, then this is not in the book, but this was in our lecture, is there a walk from A to B? And if there is a walk from A to B, I'm going to say that A is reachable from B. And because in this branch of graph theory that we're exploring in this class, where we're not looking at directed graphs, only undirected graphs, so there is either an edge between two vertices or not. And so if there is a walk from A to B, then there's also a walk from B to A. You just reverse the order. Therefore, you get that if A is reachable from B, then B is reachable from A. And also you have transitivity, so you can, if A is reachable, if you can get from A to B and you can get from B to C, then you can get from A to C by just concatenating the walks. And so what we have here, and let's just say that every vertex is reachable from itself. And so what you have is this equivalence relation. And this equivalence relation partitions the set of vertices up into equivalence classes within which all the objects are reachable from all the other objects. And we call this thing a component. So what is a component of a disconnected graph? A component of a disconnected graph is a subgraph of that graph, a set of vertices of that graph, such that within that set of vertices, all of the vertices are reachable from all the other vertices. And so that's where I'm just going to reach for sort of immediately. Then we're in this case 2 now. Then G has at least 2 components. And now the proof goes like this. And in fact, Gusset just tells us what to do. Let V and W in V, so take 2 vertices, V and W, and consider 2 cases, that they're in the same component of G or that they are in different components of G. So perhaps maybe over here to the side, I will sort of start this kind of argument. So G has at least 2 components. All right, so now I'm going to take arbitrary V and W in V. And what is V? V is just the set of vertices of this graph G. What is G? It's just a set of vertices instead of edges. So I take sort of 2 arbitrary vertices. Well, if I take 2 arbitrary vertices in this disconnected graph G, then they're either in the same component or they're in different components. So now there's sort of like a further cases. So right, there's case V and W in, maybe I'll write it up here, case V and W in same component, and there is the case that V and W are in different components. Okay, and maybe there's some pictures kind of associated with this, and here are these pictures. This is G now we're talking about, right? So here is kind of component 1, and here is V, and here is W. Okay, and great. And now there is this other, I'm seeing now, there is this other picture in which you have, these two components, V and W. You have two components, C1 and C2, and V and W are in different components. Okay, so what am I trying to show again? Perhaps I should start there. What I'm trying to prove is that, it's maybe even, would be maybe more clear if I put it sort of right here. Now my strategy, having assumed that G is not connected, is I need to show that G complement is connected. And if that's my overall goal, if I can do that, I'm done. Well, what does it mean to show that G... I'm explaining this very badly. Just backing up for a second. Goal, prove that G or G complement is connected. Well, if G is connected, we're done. Okay, so suppose G is not connected. Well, now I'm going to... Basically, this proof boils down to showing that if a graph is disconnected, then its complement is. That's the whole thing. Well, how do I show that the complement is connected? Well, to show that a graph in general is connected is to show that there's a walk between any two vertices. So that's why I'm picking two sort of arbitrary vertices, V and W here. And then these two arbitrary vertices, V and W, in G complement, in order to show that there is a walk between them, I need to consider what their status is in G. So this is the more logical way of explaining this. The reason why I've chosen two arbitrary vertices from G is because I've really chosen two arbitrary vertices from G complement. But of course, G and G complement have all the same vertices. Why have I chosen two arbitrary vertices in G complement? Because the entire goal of showing that G complement is connected is to show that there's a walk between any two vertices. So here are my two arbitrary vertices, V and W. And, well, how do I show that there is a walk between these two arbitrary vertices in G complement? I need to, it's going to depend. The logic of why there is a walk between them is going to depend on where these vertices are. And the answer is they're either in the same component of G or they're different components of G. Okay, so good. That was terrible. But anyway, we move on. In fact, I don't know why I have these like alphas and betas and stuff. Yeah. Now let's do this case first because I think it's a little bit easier. Suppose that V and W are in different components, and it's really important that we say of G, right? Because it's G that we know has two components, at least, because G is disconnected. In other words, let's suppose that these two arbitrary vertices V and W in G are in different components of G. Yeah, that's all there's to say. Well, look, if they're in different components of G, then V and W are not reachable from each other, right? So using my notation from before, it's kind of not the case that V is reachable from W. In other words, this is my notation, not from Gossett for, there exists no walk from V to W. How do I know there exists no walk from V to W in G? Because they're in different components, and then that's in fact how you construct the components as a set of vertices which are sort of not reachable from each other. If they were another way to put it is if there was a walk from V to W, then they'd be in the same component. Okay, well, if V and W are not reachable from each other, then it's certainly true that the edge itself, VW, is not an edge of G. So maybe I'll just say it like that, is not in is not in G. This is maybe the simplest way of putting it, right? That edge is not an edge of G. Because if there were an edge between V and W, then they'd be in the same component. And since VW is not an edge of G, that now, switching colors, of course, VW is an edge in G complement, because that's the definition of G complement. You put an edge when there's not one there. All right. Worst and most long-winded explanation ever. Anyway, there it is. I connect, and am I just done? I'm just done, right? What have I just shown? I'm done with this case. So there is a walk from V to W. So there is a walk from V to W in G complement. All right, what about the case in which V and W are in the same component? Well, now what I have to do is I have to say, well, so far it doesn't. This doesn't seem to work. In fact, if V and W are in the same component, do I know whether there is an edge between V and W or not? No, I don't. Right? There might be an edge between V and W. That's certainly something that could be true if two vertices are in the same component. But it's also possible that there's no edge between V and W, but instead, there is a sort of a longer walk from V to W via some other vertices, okay? So actually, the precise relation between V and W, if they're in the same component, is unclear to me. This is still G I'm talking about. But now I invoke the fact that there is at least one more component, right? Why? Because I know that G is not connected. So if there is at least one more component, then let's take a vertex X, an arbitrary vertex X in some other component. And now I just kind of repeat the logic, right? If X is in component 2 and V and W are in component 1, then once again, by the definition of component, it's not the case that V is reachable from X. In other words, there exists no walk from V to X. It's also not the case that there is a walk of any length from W to X, because they're in separate components. Well, if that's true, then of course Vx, the edge Vx itself, is just not in G. And also the edge Wx is not in G. But if those edges are not in G, then they are in G complement. And so there actually must be, in the complement graph, edges between every pair of vertices which are in opposite components. That's another way of thinking about it. So edge Vx is in G complement, and edge Wx is in G complement. And now, just take the walk, V X W is a walk of length 2 in G complement, from V to W. All right, so what have I just shown? I've just shown that for every, so maybe conclusion over here, take VW and V, see these two cases, then there is a walk from V to W in G complement. That walk is either of length 2 if V and W are in the same component, or that walk is of length 1 if V and W are in separate components. So by the definition of G complement is connected. All right, that was like 15 minutes instead of like what should have been 5 minutes, but I guess I got the job done. More, let's go a lot faster now if we somehow can. Hopefully I think that's clear. All right, next, the rest of these problems are just do-it problems, although that doesn't mean they're necessarily easy. This is just pure vocab, man. They say, all right, hey, I gave you a bunch of walks. Just get all this crap straight in your mind. Trail, path, close walk, blah, 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 blah. We begin. This is 3A. So here's the graph. This is the famous Euler graph. The bridges of Königsberg graph. Okay, so this says start at B. So let me put a little green arrow here or something at B. And now do the following. Go from B via E3. So I'll just maybe make this like red or something, and then like an arrow to C, of course. And then by the time you get to C, follow then E7, and then you're at D, and then follow E5. Jump, and then you're at A and then stop. Okay, this is pretty boring. Is this a trail? What's a trail? Trail, ET for VP. This is the only way I can remember this. I kind of just know what a trail is, but all right, what is a trail? It does not reuse edges. And so is this a trail? Yes, because I do not reuse any edges. I use edge E3, E7, and E5 once only. That's it. Is it a path? What is a path? A path does not revisit any vertices. So yes. Is it a closed walk? No, because I started B and ended A. So no. Is it a circuit? No. What is a circuit? A circuit is a closed trail. Yeah. A circuit is a closed trail. Well, then it's certainly not a closed trail because it's not even closed. And is it a cycle? Also no, because a cycle starts and ends at the same vertex and visits every vertex exactly once except for the first and last vertex. Okay, that was pretty easy. Same graph. Look at all this preparation. I put hours of effort into this crappy YouTube video. What is this other walk? Well, now we start here at D. And what are we going to do? Well, we're going to, we're going to start here at D. Then we're going to follow E6. So we do that. And jump. And then we get to B. And then B, we follow E4. And then we get to C. And then we follow E7. Ooh, this is getting kind of exciting. And then we're back to D again. So, is this a trail? Yes, because it does not reuse any edges. Is it a path? No. Hold on, I need to make sure I say this correct. Yeah, no. It's not a path because a path, I'm like somehow doubting myself, but of course I know what I'm talking about. A path is a walk with no repeated vertices, but this just straight up does have a repeated vertex. That is D. But it kind of like, okay, well anyway. Is it a closed walk? Yes, because I start and end at D. And is it a, in fact, if you're a closed walk, then you start and end at a certain vertex, then you sort of can't be a path. And therefore, there is sort of no such thing, technically, as closed path. That's kind of a contradiction. If you take this very technical definition of path, which is that no vertex is sort of revisited. And so, yes, it is a cycle, because that's actually just exactly what a cycle is, right? A cycle is a walk, a closed walk, in which the only revisited vertex is the first and last one. And is it a circuit? Also, yes, because it's a closed trail, which is to say that it's closed and it does not reuse edges. Okay, so actually that was totally worth it, but should have been done 2 weeks ago. Oh, more. Great. More practice. Same thing. V3. So if you actually did this homework like on time, right when it was assigned, then it would be very, very helpful for like the following class to have done all this work and to have all this vocabulary very, very clear in your mind. But anyway, here we are 2 weeks later. So V3 to E, let's just do this with less commentary now. V3 via E5 to V2, and then via E4 to V4, and then via E3, back to V. What the hell just happened? Back to V2, and then we sort of stop. So maybe I'll write something like, stop there and start here. And now I think that's just pretty clear what happened, right? We went jump, jump, jump. Okay. Well. What now? Oh man. What now? Is it a trail? A trail does not repeat edges, and this does not repeat any edges. So yes is the answer. For some reason, yes. Okay, is it a path? A path does not repeat vertices, but this does repeat vertices. So this is not a path. In particular, V2 is like repeated, right? Okay, is it a closed walk? No, because it does not start and end at the same vertex. It starts at V3, but it ends at V2. Is it a circuit? No, because it's not closed. A circuit is a closed trail. Yeah, and this is not even closed. Is it a cycle? Also no, because a cycle is also a closed thing. It's kind of a closed path. Well, whatever. You know what a cycle is. So no, it's not a cycle because it's not closed. Okay, one more. V2, I begin here. And we got a little bit of this going on. And what do we do? It's getting more complicated, I guess. V2, so via E3 to V4. And then from V4 via E2 to V5. And then via E1, yikes. Back to V4. And then E4. And then back to V2. So now this one just goes like wah, 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 wah. Okay, so this one's kind of interesting, maybe. Is it a trail? Well, ET for VP. Is it a trail? Yes, because no edges are repeated. You can simply see that the 4 edges used are E3, E2, E1, and E4. It's actually very nice in this linear representation. So it is a trail. Is it a path? Well, certainly not, right? Because vertices are definitely revisited. V4 is being used multiple times. So this is not a path. Is it a closed walk? Yes. That can be seen very easily by seeing that we start and end at V2. Is it a circuit? Yes. And this is exactly the kind of, and it's not a cycle. And this is actually the perfect case of something which is a circuit but not a cycle. Why is it a circuit? That's because a circuit is a closed trail. It is a trail because we don't reuse any edges, and it is closed. But it's not a cycle because in a cycle you only visit each vertex once, not counting the first and last vertex. So this is basically a figure 8 type situation, and I try to encourage you to sort of think of this as the classic example of something which is a circuit but is not a cycle. It's just really the difference between the two. Okay, once again, valuable, I guess, to spend time on that kind of thing. Okay, what is the connectivity and edge connectivity for the following graphs? All right, this is kind of like a hard thing or whatever. What is connectivity and edge connectivity? Connectivity, the actual definition is, maybe I should have thrown this up onto the thing. Let's see, is it too late to do that? Never, it's never too late. All right, let's see, let's go up a page or so. Since this is already not an efficient video, so let's just make it thorough. Boom. So what is connectivity? A graph has a certain connectivity if K is the size of the smallest subset of vertices whose removal from V either causes the graph to become disconnected or reduces V to a single vertex. Okay, so basically, as I explained in class, it is if you think of vertices as people and the edges between them as friendships, then it's how many vertices do you have to remove in order for the graph to become disconnected. So how many people need to move out of town in order for your class to be no longer connected via a sort of a network of friendships. And it's specifically the minimum number. Okay. And so it's kind of a measure of how connected your graph is. If K is quite large, then, I mean, the sort of idea here is that even a connected graph, perhaps a graph which is, even like very connected, like maybe you have like a K5, that's a lot of connections. Every single person is friends with every single other person. And imagine there's another piece over here that's also K5, and jump. And then these two people are friends. Well, there are a lot of friendships in this class, but actually, or maybe we'll even just do this. Yeah, how about that? It turns out that there's just kind of like one person holding this class together, and that's this person right here. So this graph is in some sense very connected, but in other sense it's not connected at all. If this one vertex were to leave, then if you delete this one vertex, then suddenly your graph is disconnected. And so we would say that this vertex has connectivity 1. Okay, that's kind of the idea. And it's sort of obviously, this is kind of an important thing. If you're building, say, you're trying to build some sort of robust, computer network, say, for example, of information being sent, between many computers, then this is the kind of thing you want to have, high connectivity. Because here, if you are, I don't know what you would be doing, but if you're sort of sending packets of information between hundreds of different computers and your graph has connectivity 1, well, that's terrible. That means one person turns their computer off and suddenly you can't get the information you need from person to other person. Or if this is a bunch of cities and the edges between them are roads, then if your road network has connectivity 1, it's also really bad. That means all it takes is, one city to disappear, and then suddenly you can't get any more from city to city. Okay. Some city goes into quarantine or whatever and cuts off all roads from that city to everywhere else, and then suddenly your whole country becomes disconnected from each other. So this is very important. All right, let's just do it. That being said, there's no real, well, at least in this book, in this class, we're not exploring any real algorithms for this. So I'm not going to really explain to you how to do this in general. I'm just going to tell you that, like, yeah, I looked at it for a while and I've decided what the answer is. Oh, so wait, that's connectivity. Then what's edge connectivity? Edge connectivity is just something else. Edge connectivity says, boom. Oh boy. All right. Excellent video. Yeah. So hopefully that's coming up. I bet it is. So what do we have here? Edge connectivity is sort of the other notion. Now we are measuring how connected the graph is, not by the nodes but by the edges. And so now we get now this is sort of the other thing now I was talking about, right? Wherein now you have once again maybe a K5, and then you have another K5, and yeah. And now imagine that there's just sort of one friendship connecting them. So now, previously we referred to this as like the sort of important vertex or the fragile vertex. Well, this is now kind of the fragile edge, but the idea is still the same, right? If you remove this one edge, then suddenly your graph is disconnected. So now this is maybe better now to talk about this with respect to the road situation, because now you can sort of say, yeah, you have a bunch of cities and a bunch of roads between them. If one road breaks down because of snow or avalanche or rocks or whatever, then now suddenly you can't get from place to place. So this is another measure of how connected a graph is. And yeah, there it is. Okay. And then there's this other sort of bit of vocab, which I definitely didn't even mention in class, which is we say that a graph is K connected if the connectivity is at least K. And so this would be an example of a 3-connected graph. This is a 3-connected graph. Why? Because in fact, the answer to this question is what are we supposed to be doing? What is the connectivity and edge connectivity? Well, my answer is that the connectivity is 3 here. How do I know that? All right, well, here it gets maybe a little bit kind of complicated or something. Here I now have prepared, but I don't know how useful it is. This is the Peterson graph. This is kind of a famous graph, this Peterson graph. Very interesting. And, well, what is there to say about this graph? First of all, this graph is highly regular. That is to say, it is sort of obvious that along the outside that the 5 vertices are all kind of the same. Rotate this by 72 degrees or 360 over 5 or whatever, and you see that it's all the same thing everywhere. So you might think initially that there was some difference between being an inside vertex and an outside vertex, but that is wrong, because in fact I can perform some kind of inside-out maneuver and take all the points of the star to the outside and bring all the... No, I guess I need to do a little bit more than that. So drag, and then D is connected to C, and C is connected to B, and B to A. So now, what have I just done? I have just shown, almost, we're getting there. What the heck? Oh, okay, hold on. Being dumb for a second. H and F and J. Boom. It's the Peterson graph again. Whoa. In other words, you can perform this kind of inside-out maneuver in which the points on the outside become the points on the inside, and the points on the inside becomes the points on the outside. So in fact, this graph is kind of like just 2 cycles of length 5 with certain sort of additional connections. That is to say that there's not only nothing special about being a point, being one point on the outside versus another point on the outside, but there's also nothing special about being a point on the inside and a point on the outside. In other words, this graph is just completely regular. And if this graph is just completely regular, then I can perform my analysis on any one vertex, and it's just the same as any other vertex. And what am I supposed to be doing? I'm supposed to be figuring out the connectivity. Well, what does that even mean? That means how many vertices do I have to remove in order for this graph to become disconnected? And I just have to remove a lot of vertices for this graph to become disconnected, because there's just no way to do it, man. Take any vertex E. It's just connected in a kind of a way to sort of 3 other vertices, and there are no sort of like weak points in this graph whatsoever. And so the only way to make this graph disconnected is to delete, the 3 vertices that are adjacent with E. So say A, I, and D. And now this graph will become disconnected. In other words, the only way to make this graph disconnected, or the shortest way to make this graph disconnected, is to simply isolate a vertex by removing all the edges incident with that vertex, by deleting all of the other vertices on the other side of that edge. All right, and you can kind of explore, random other ways. So okay, what have I just shown? I've just shown that it is possible to disconnect this graph with the removal of 3 vertices. Now, the claim that this graph is in fact 3 connected is a stronger claim. The claim I'm making now is that, and this is what it's quite hard to prove, and it's beyond the scope of this exercise to actually prove this, but if you want to prove that this Peterson graph is 3 connected, then what you have to prove is that it's not possible to disconnect this graph by removing fewer than 2 vertices. And so, okay, removing any one vertex, clearly this graph will still be connected. So now you have to say to yourself, okay, is it possible to delete 2 vertices somewhere on this graph and to make this graph disconnected? And the answer is just kind of like no, right? I mean, look, let's just go through it. Suppose you're on the outside. Is it possible to delete 2? What if I delete 2 consecutive vertices? Is that going to make the graph disconnected? No. What if I delete 2 vertices that are off from each other by 1? Is the graph disconnected? No. What about if they're off by 3 from each other? Well, if they're off by 3 from each other, then that's the same as being off by 2. So, okay, that's that. What if I remove a vertex, and then the outside is the same as the inside, so that's done. What if I remove a vertex on the outside and a vertex on the inside? Well, if they were the two that were adjacent to each other, then the graph is still connected. What if I remove one on the outside and a different one on the inside, like E and H, say? Well, the graph is still connected. And I think I'm just kind of done, right? Because maybe E and G are somehow different, but they're just not. So, okay, I've just shown you by a pretty exhaustive search with invoking some symmetries that for any two vertices that I remove from this graph, the graph will still be connected. And that by the combination of that with showing that that I can remove 3 vertices and make the graph disconnected, that's what justifies my claim that the connectivity of this graph is 3. Okay, what about the edge connectivity? Well, okay, now we have to delete some edges. How many edges do I have to delete in order for this graph to become disconnected? Well, once again, it's pretty clear that if I delete 3 edges, then the graph is disconnected because now I have a component with just E in it. So now the question becomes, is it possible to do it in fewer than 3? Can I delete 2 edges in some kind of a way such that this graph will be disconnected? And the answer is just no, right? Because no matter how I do it, I mean, every vertex just has too many edges coming out of it. So if I delete an edge here and I delete an edge here, it's still totally connected. If I delete 2 edges that are incident with a single vertex, then it's still connected. And so, yeah, the answer is just no. And therefore, I claim that this is not only 3 connected, but that it is also, because there's this other piece of K edge connected. So it is 3 edge connected as well. Okay, so that was maybe a little bit fun, but maybe a little bit not fun. Edge connectivity 3. I think we've now explored this concept pretty seriously. Okay, good. Woo. Geez. Okay. Continuing, what about this goofy graph over here? Well, believe it or not, I have made this goofy graph, and here it is. What is the connectivity of this graph? How many vertices do I have to remove for this graph to become disconnected? I guess the answer is 2. The removal of no one vertex will disconnect this graph. Watch. Boom, still connected. Remove 2, still connected. Remove 3, still connected. This is beautiful. Remove 4, still connected. Remove 5, still connected. Remove 6, still connected. Remove 7, still connected. Remove 8, still connected. And remove 9, still connected. So, but can I remove 2 vertices and disconnect this graph? Easily, I can. For example, if I remove vertex 2 and vertex 4, 3 only had 2 connections. So if you remove the 2 vertices adjacent with 3, then certainly that's going to be the case. And so, in fact, there's kind of this theorem. So all right, so well, let's just go back and summarize. What have we seen here? We've seen that the connectivity of this graph is 2. Because 2 is the minimum number of vertices that I have to remove in order to make the graph disconnected. And in fact, I can say something stronger here, which is that notice how I sort of focused my attention on this vertex number 3. Why? Because its degree was 2. And so, in the book, Gossett even defines, hey, let delta be the degree of the minimum degree vertex. So let it be the sort of the minimum of the degree of every vertex in this graph. So take the degree of every vertex in this graph and let a delta be the minimum of all of those degrees. And then what did he say? Connectivity K and so yeah. So basically, it's like this: the the degree of this minimum degree vertex has to be greater than or equal to the edge connectivity, which has to be greater than or equal to the connectivity. Which is to say, here we saw that, how can I put this? The best way of putting this is, if you have a vertex that only has degree 2, then you can certainly make the graph disconnected by just removing the 2 vertices that are incident with the edges incident with that vertex. Okay, so that's what we did, right? We looked at 3. We saw that 3 has degree 2, so there are 2 edges which are incident with vertex 3. And if we remove the 2 vertices on the other sides of those 2 edges, then we've disconnected the graph. And so it certainly can't be the case that the connectivity of the graph is more than the degree of the minimum degree vertex. And then for edges, it's kind of the same thing, right? Here, if we remove these 2 edges, then we have disconnected the graph from this vertex 3. And so once again, and now what explains this relationship, what explains sort of this part? Well, this part is explained, I guess, by saying that if you remove some maybe I don't feel like explaining this right now. Let's actually compute the edge connectivity for this graph, and then we'll go back and talk about it. So here we are, back to here. The question is, how many edges do I have to remove? And the answer is, once again, 2. I can just remove the 2 edges that are incident with vertex 3. So why? So this graph just does have edge connectivity equal to 2 also. So that's maybe like a little bit boring. The answer is, how does this work? The answer is that even if you remove 2 edges, you might not make the graph disconnected if, this is kind of a bad example of this, because here when you remove those 2 edges, you do disconnect the graph. But it's possible, I'm looking at kind of a counterexample in Gossett right now that he has on page, this is his, if you're still watching this video, this is his explanation right here, is via this little graph. So this little graph was meant to illustrate this principle to him because, and let's now just maybe do it really fast in blue. What is delta in this case? Well, in fact, there's no vertex of low degree. So delta is actually just 4 in this case, because there is, every vertex has at least degree 4, maybe even higher, maybe 5. 1, 2, 3, no, 4. There is one of 4. But that, now what's the edge connectivity? Well, how many edges do I have to remove in order to disconnect this graph? It's clear that the weak link is kind of like around here, right? In between these sort of 2 almost K5s. But to actually disconnect this graph, if you just remove this edge, it's not disconnected yet. If you remove these 2 edges, it's also not disconnected yet. So you need to actually remove all 3 of these edges. And so the edge connectivity in this graph is 3. But the vertex connectivity in this graph is in fact 2. Because if you simply kill, say, this vertex and this vertex, then you've removed all the part of the graph on the left-hand side. You've disconnected it completely from the part of the graph on the right-hand side. So this is a case in which the connectivity is 2. If 2 cities go into quarantine, your country is now disconnected. The edge connectivity is 3. If 3 roads go down, if it's these particular 3 roads, then your country is disconnected. But in fact, there are at least 4 roads out of every city. So the degree of the minimum degree vertex is 4. Okay, this is just extreme, too much detail. And now we have just like yet a whole nother problem. So I don't really feel like doing this problem is what it comes down to. Did I name this graph? I did. So this is the graph. What is the connectivity in this graph? It's just 4. It's just 4 across the board. I'm not 100% positive, but I think that is just true. That here, the connectivity is 4 because in order to disconnect this graph, we really just do have to delete 4 vertices. I hope that's just true because if it's not, I'm just dumb. And the edge connectivity here is also 4. And this graph is highly regular. Again, the degree of every vertex of this graph is 4. This is in fact a 4. This is a regular 4 graph, but it's also a 4 connected graph because the connectivity is 4. Okay, let's move on. Okay, right. Then we have this other new piece of vocab, this idea of a cut vertex. This actually would have been useful for some of our conversations on the previous slide. What's a cut vertex? It's the vertex which, if you remove it, then the graph becomes disconnected. So it's the city which, if the city goes into lockdown and closes all roads into and out of that city, then the countryside is now disconnected from each other. So there it is. Boom. And what is a cut edge? A cut edge is the corresponding concept that it's the road which, if you close that road, then the countryside becomes disconnected. Of course, if it was connected already. Okay, so this proof is that this isn't even really a theorem. This is kind of just definition bookkeeping. You have a simple graph with a certain cut vertex. So what does that mean? That means G is connected. But if you remove, and maybe I'll just write it like that, since that seems to be a decent notation. Just what is G minus V? It's the new graph that you get by taking graph G, removing vertex V, and all edges incident with that vertex, is disconnected. Okay, that's just what it means for V to be a cut vertex. So prove now that G complement minus V is connected. Okay, well, what is, so I have G is connected, G complement is disconnected. I think this is just an application of that first theorem from the beginning of this video. So if G is connected, what can I say about G complement? G complement is disconnected. Is that what I want to say? No, that's actually just not even true. Sorry, hold on. Let me collect my thoughts for a second. Prove that G complement minus V is connected. Okay, well, what is going on? Let's make a picture. Here is the picture. G looks like this. And G minus V must have some components, at least 2. So there are at least 2 components, C1 and C2, and because this graph is disconnected, and it sort of must be the case that, well, pictorially here, it must be the case that this vertex V that we deleted had to be either sort of outside of components V1 and V2 but with connections to both, or possibly inside component C1 or sort of inside component C2 in a certain kind of way, such that removing it was that was the only connection to the other vertices in component C1 and C2. So hopefully this picture makes some kind of sense. And now, what can I say about G complement minus V? Well, I have to sort of complement first and then remove V. What am I trying to show? It's connected. Maybe the best thing to do is just go straight for the proof and let the math do it. So how do I show that this graph G is disconnected? I just take is connected rather. I take 2 arbitrary vertices, U and W, in the graph G complement minus V. And I want to show that this graph, G complement minus V, is connected. And so I want to show that there is a walk between U and W. Wait, I really do feel like this is a one-line proof that I can use the previous thing, right? Because, oh, I see. So, yeah, what you have to, well, okay, this would be the long way. Show that there's a walk between U and W. I guess I don't want to do all this logic again, because all the logic again would now involve sort of the two cases, right? Is it true that U and W are in the same component of G? And if they're in the same component of G, then there is a walk. Yeah, the way to do this is to apply some kind of theorem that says that the complement of G minus V is, in fact, G complement minus V. Is that even just true? Hold on a second. So take a graph G and remove vertex V. So that removes vertex V and all the edges incident with vertex G. Sorry. Take a graph G and remove vertex V and then remove all the edges incident with vertex V. Done. Now take the complement. What is the complement of that? The complement of that will be it will be what it is, okay? But over here, what do I get? I get the complement of that is going to be, you know, there'll be edges between all the other vertices if there weren't already. But over here, I take first now G complement, but that now is yeah, and then I remove vertex V from that complement. And so, yeah, either way, you're just, when you remove vertex V, it doesn't matter whether you remove it at the beginning or you remove it at the end. By removing it, you remove all the edges incident with it. And so this just is true. And since this just is true, then I really can just apply the theorem from the beginning, right? That I know that this is connected. I know that this is connected because I know that this is disconnected. Sorry, I know that this is connected because these two are the same, and I've shown in that very first problem from the homework that if that either a graph or its complement is connected. And so by showing that this is disconnected, I know that this graph is connected because this is just the complement. So is there a better explanation for this? I guess neither of these graphs have V in it. So both of these graphs, I'm just trying to give a better explanation for why these two are equal. It's kind of obvious, but explaining it precisely, well, I guess you just do this, right? Take two arbitrary vertices, U and W. Is there an edge between them in G? Well, suppose there is an edge between them in G. Then there isn't an edge between them in G complement. So if this is a picture of what the G graph looks like, this is a picture of what the G a local picture of what the G complement graph looks like with no edge between them, and then therefore removing vertex V from G complement doesn't change the fact that there's just no edge between U and W. So, what have I just shown? I've just shown that take a graph G, remove vertex V, remove all edges incident with V. What do you get? Well, I don't know what you get overall, but between any two vertices U and W that are not V, if there was an edge between them, then there just still is. And so when you perform the complement operation on that entire graph, you're sort of performing it on every edge that's left over. And so you perform it on this UW edge, then there's no edge between U and W and G complement. And so it sort of doesn't matter whether you remove V first and then complement versus complement and then remove V. Okay, this is just a waste of time. All right, let's do these last three problems. We're going to do the adjacency matrices for these following graphs. I'm now like so tired. I want to be done with this homework. So here we go. A, B, C, D. And I'm going to just say how many vertices there are between them. Well, there are. How many edges are there from A to A? None. How many edges are there from A to B? 2. How many edges are there from A to C? None. How many edges are there from A to D? 1. How about from B to B? None. How about from B to C? 2. How about from B to D? 1. How about from C to C? None. How about from C to D? 1. Yeah. How about and then from D to D 0. So that is the adjacency matrix for this graph. Okay, over here I have V1, V2, V3, V4, V5, and V6. And over here V1, V2, V3, V4, V5, V6. Cha 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 cha. Beautiful. Okay. Edges, so 0 from V. This is going to take forever. From V1 to V2, there's 1 edge. From V1 to V3, and that's just it. There are no other edges between V1 and anything else. How about and then this will just be the same because it's totally symmetric. How about now V2? Well, there's an edge to V1, check. There are sort of 2 edges, so to speak. We've already discussed this from V2 to itself because that's what we're going to counter loop twice. There's an edge. There are no edges to V3 or V4, but there is one to V5 and there's none to V6. In fact, V6 just has degree 0. So this is all that. How about from V3? There's an edge to V4 and V5, and that's it. And no others. So ja. And from V2 to V4, there's nothing. And from V2 to V5, there's 1. From, yeah. And how about now from V4 to V4, no. From V4 to V5, yes. So yes. And from V5 to V5, no. Okay, so that is the adjacency matrix. And why is this kind of nice? Well, reading across any row, you see what the sum of all those numbers is the degree of that vertex. So degree of V1, degree of V2 is 4, degree of V3 is 2, degree of V4 is 2, degree of V5 is 3, and degree of V6 is 0. Okay, last problem from this homework, but it's going to take us a minute. Create the adjacency matrix for the... Did I just kind of already do this? I totally just did this already. It's kind of annoying. Well, I'll just kind of like do it again really fast or something. Well, I really just did already do it. So maybe I want to now just do something like just copy this and yeah, boom. Okay. Well, take it, as they say, from 7a, and now we're going to apply this theorem. And this theorem says that you want to calculate a cubed. All right, well, for this I'm going to use some kind of online features, and this seems like a good way to do this. So here I'm going to make a new matrix, and I want this matrix to be 4 by 4. This is just using Desmos. So 0, what happens if I hit enter? Nope. Didn't like that. 0, 2, 0, 1. 2, 0, 2, 1. 0, 2, 0, 1, and finally 1, 1, 1, 0. Okay, so enter. So this is my matrix A. Have I entered it correctly? I have. This is just like what you would do on a graphing calculator, but sort of better. And now I want to do A. No, I want to do A. That's interesting. I want to do A cubed. Boom. So I get this crazy thing. What is the significance of this little matrix, which I now copy? The significance of this matrix, we proved in our theorem, is that it tells you now for every pair of vertices what the number of walks are from that vertex to another vertex of a certain length. And so this is A, B, C, D. This is A, B, C, D. And so what are we supposed to do? How many walks of length 3 are there between vertex A and vertex D? The answer is there are 11 of them. Oh man. All right, so without further ado, I shall now list, and then this video will be over, the 11 walks of length 3 from A to D. All right, let's go. I can go from A. Let's just do it with edges only. That'll be fast. So starting at A, I can do E5, E5, E5. In other words, just go jump, jump, jump. That's a walk of length 3 from A to D. All right, that was fun. I can do E5, E6, E6. In other words, there, back, and back. I can do E5, E7, E7. Okay. I can do, and then I guess there's going to be more of those, right? Hold on a second. I see. So is that really just it? So okay, well that's one. Oh no. So E5, 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 E6, E7, or sorry, E5, E6, E6. Okay, I guess I'll just keep going. I can do E5, E7. No, I did that already. Oh my gosh. What else is there? Okay, let's do. Okay, so let's do E1. So if I go E1, oh, okay, I see. So I can do E1, E2, E5. E1, E2, E5 is a walk of length 3. I can do E1, E4, E7. I can do E1, E3, E7. Or I can do... This is not very systematic what I'm doing here. E5, E5. Yeah, I don't know. Okay, that's 6. There's 5 more apparently. Well, I can repeat that all over again, right? I can do E2, E1, E5, or I can do E2, E3, E7, or I can do E2, E4, E7. But there are apparently 2 more. What are they? Am I just being dumb? Walks of length 3. E2 walks of length 3 from A to D. I'm missing something. Oh, because duh. I could also do E1, E4, E7, And I can also do E2. No, I covered that already. Hold on a second. Completely brain dead right now after making this video. I'm just feeling so dumb. So wait, let's just try to finish this. What is it? E5, E5, E5. E5, E6, E6, E5, E7, E7, E5. People at home are just going to be laughing at me, but I refuse to give up. E1, E2, E5, E1, E4, E7, E1, E3, E7, E2, E3. What can I possibly do? The walk has to either start with E5, E1, or E2. Fact. Oh, duh. No. 2, 1. What is going on? E1, E4. Okay, let me just be more systematic. I have sort of 3 choices. If I follow E5, then I'm already at D. And the only way to get back to D is to just leave D and then return from the same route. So I feel like that's covered if I do E5 first. If I do E1 first, then I'm here at B. Well, I have 2 choices. I can't go straight to D because then I have to get back to D in only one step. So from E1, I have 3 choices. I can go back to E2, but then it's determined, or to E3, or E4, and then it's also determined. So I actually just straight up don't see how there is 11. I've done this problem before. Walks of length 3 from A to D. I'm just getting completely paranoid now, right? From A to D is 1. Is this adjacency matrix wrong? It just can't be. 0 from A to B is 2. From A to C is 0. From A to D is certainly 1. So yeah, 1, 2, 3, 4, 5, 6, 7. The adjacency matrix is right. The calculator is just also right. Everything is right. The math is right. My brain is wrong. I should just end this video, but that would be embarrassing. What are the other 2 freaking walks, man?